Quicksort. Quicksort is a divide and conquer sorting algorithm with a lot of specialities. The main speciality is evident from the name itself. What does the name say? Name says quick sort. The reason it is called quick sort is that it is very fast in all practical scenarios. The reason why I am stressing on practical scenarios is that if you see the worst case time complexity of quicksort, it is order of n square. So looking at this worst case time complexity, you may feel like this algorithm is not so fast, but that is not true. This worst case time complexity of order of n square, this is hit in very rare scenarios, and you can say practically this would generally not be hit at all. So in all practical scenarios, quicksort works in order of n log n, which is the average case time complexity of quicksort. Moreover, it is proven that quicksort works faster than other n log n algorithms like merge sort in most of the scenarios. So this is why quicksort is generally the go-to option whenever you want to do sorting faster, especially when your data is very large. So this is why quicksort is important, because whenever you look into any sorting algorithm, the main consideration is that your algorithm should be able to run faster than other algorithms. So this is where quicksort comes handy. So naturally the next question is, how does quicksort do this sorting? So it sorts an array by choosing a pivot element from this array and repeatedly partitioning the array around a pivot element. This is the basic logic. Let us understand this in detail. What it does is, if you have this as the input array, it will initially choose a pivot element. It is a convention that generally you choose the last element of the array as pivot. See, whatever element you may choose, as per your wish, it is still the same quicksort algorithm, but generally you have a convention that you will use the last element of array as the pivot. So once you choose the pivot, what you do is, you will see which is the correct position for the pivot if this is completely sorted. So when you build completely sorted array, what should be the right index of this pivot? Whatever be the right index, you will place this pivot element in that index. This is the first step in quicksort. Once you place pivot element in the correct index, there are two more things to be considered. When you place this pivot here, it is not just that you place pivot here, but also you will place all elements that are lesser than pivot on the left side of pivot and all elements which are larger than pivot on the right side of pivot. See, this part won't be sorted, but all those elements will be lesser than the pivot. Similarly, right side of this pivot won't be sorted, but all those elements will be larger than whatever is the value of pivot element. So at this point, given that you already put pivot in the right position in sorted array, and you know that whatever is in the right side of pivot, that are supposed to be on the right side of pivot itself in the sorted array, and whatever are there in the left side of pivot, they are supposed to be in the left side only in the sorted array. What can you do? You can recursively run this same algorithm separately on these two separate parts. Because you already placed pivot correctly, you know this complete part will stay here only, but this should be sorted. That is the thing you have to do. So you will recursively call the same quicksort algorithm multiple times on this side. The next question is, what procedure do you follow in order to place pivot in this correct position, and at the same time to find all the elements smaller than pivot, move them to the left side, and find all the elements larger than pivot and move them to the right side. So for this thing, what is the procedure that you are going to follow? That is what we'll look next. So the procedure you are going to follow, it's very simple. First, you choose a pivot element. Let us say the last element is only your pivot. You'll have two pointers. One pointer will start outside the array, just outside the array, that is one step outside the array. That is where your first pointer is. Your second pointer is in the first element of this array. So let us just put all these elements here. So your second pointer, this is on the first element of array. What your second pointer will do, it will go through all the elements one by one till it reaches the last element. Last means second last element, because last element is your pivot. You don't have to come back to this. So when it goes through all these elements, it will check whether those elements are larger than pivot or are they smaller than pivot. In case they are larger than pivot, you know that element should be placed on the right side of pivot. So in that case, you can simply go forward to the next element, because if it is larger, you are not going to touch it all. The reason is, finally what you are going to do is, you are going to place this pivot in front of all these larger elements, right? So because of that, if you know the element is larger, you are not going to do anything. But in case the element pointed by this is smaller, let us say it reached here, and you found an element which is smaller than the pivot, then what will you do? Because it is smaller, it should be placed before the position you are going to place pivot. So that is what this pointer is tracking. This pointer will track the point till which all elements are smaller than pivot. So after this point, all elements will be larger than pivot. So till this point, you have not seen any elements which are smaller than pivot. That is why this point is standing outside the array. So whatever is in the array till this point are larger than the pivot. But at this point, you found an element which is smaller than pivot. So what will you do? You will first increment this pointer to the next one. Then you will swap the elements in these two pointers. When you swap, what happens? This element you know is larger than pivot. So that will come here. And whatever was here, you know this is smaller than pivot. So that will come here. Which means till the point pointed by this first pointer, you will have elements which are smaller than pivot. After that, all elements will be larger than pivot till the point you are having this current pointer. Again, you will go take this current pointer forward. You will do the same process. You will check whether it is smaller or larger. Again, you will move forward. Let us say this is also smaller. Then what will you do? That is smaller than pivot. Then you will again increment this pointer and swap these two values. When you swap, whatever is here will come here, whatever is here will come here. Then at this point, you reached last element before pivot. So the remaining element is only pivot. So you should not take this pointer to the pivot. What will you do now? You will increment this pointer again and swap with pivot. What happens now? This pivot, this will be placed here. So at this point, pivot is placed here, and you know all these elements are larger than pivot, all these elements are smaller than pivot. What can you do now? The same algorithm you can recursively run on this subset and also this subset. So this is the quicksort algorithm. What we'll do, we'll take numbers and we'll have a dry run so that the algorithm is very clear for you. So this is our array. So we are going to take the same numbers as always, because I want you to understand how exactly this algorithm is working at each pass and how it is different from all the other algorithms that you learned. So that is what I want you to understand very clearly. So that is why I am taking same numbers in all examples. That is examples of all sorting. First digit is 42. 42. Second is 70. Third is 12. Fourth is 30. And fifth is 24. So this is your array. I'll index as 0, 1, 2, 3 and 4. So you have two pointers now. First pointer will stay outside the array. Second pointer will stay at the first element. In your first pass, you will choose 24 as the pivot, because 24 is the last element in your array. So that is your pivot. What will you do now? You will first consider 42. Is 42 lesser than 24? No, it is not. So you will take this forward. Is 70 lesser than 24? No, it is not. So you will again take this forward. Is 12 lesser than 24? Yes. So you found an element which is smaller than your pivot. What should you do? You should increment your left pointer and swap the elements in left and right pointers. So 12 will come here, 42 will come here. Next, you will again increment this pointer See whether 30 is smaller than 24. No, it is not smaller. You don't have to do anything. So when your pointer reaches here, you know only pivot is remaining. So you don't have to increment any further. What will you do? You'll increment left pointer and then you will swap pivot with whatever is present in left pointer. So 70 will come here. 24 will come here. So 24 was your pivot, and what have you done? You placed your pivot element 24 at the correct position, plus whatever is lesser than 24 is at the left side of 24. Whatever is larger than 24 is in the right side of 24. But this subarray is not sorted, but it is just that all the elements are larger than 24. You know that. What will you do now? Your first pass is done. First pass is done successfully. What will you do now? You will run the same algorithm separately on the left side and the right side of pivot. So on left side you have only one element, so you don't have to run anything because one element is by default sorted. There is nothing to compare with. So you will run quicksort algorithm on the right side, right subarray. So what will you do here? Your one pointer will be staying outside your subarray. Your subarray is starting from here. Second one will be at the starting of subarray, and 70 is your pivot. What will you do? You will check whether 42 is smaller than 70, and is it? Yes, 42 is smaller than 70. What will you do whenever it is smaller than 70? You will increment this pointer. Both are pointing to the same, and then you will swap. So here there is no swap to be done because both are pointing to the same. So you will then increment this again. What about 30? 30 is also smaller than 70. So what do you have to do? You have to increment this pointer, and then you have to swap the values in left and right pointers. But in this case again, left and right pointers are pointing to the same element. There is no swapping to be done. So you will increment your right pointer again. So right pointer has reached the pivot, so you can stop here. What will you do now? You have to increment left pointer and swap whatever is there in left pointer with the pivot. So you are standing on pivot itself, which means there is nothing to be done. What will you do? You are done with this particular pass. Your pivot 70 is placed in the right position. So what did you understand now? 70 is placed in the right position when you were trying to work out this subarray. So the only remaining part is this part where you have 42 and 30. You have to run the same quicksort algorithm here. What will you do? This is your total array of size 2. Left pointer is placed and outside of your subarray. Right pointer is placed on the first element. 30 is your pivot element. What will you do now? You'll see whether 42 is lesser than 30. Yes, 42 is less. No, it is not lesser than 30. 42 is larger. What will you do? You'll simply increment this pointer. You have already reached the pivot, so you don't have to do anything else. So how are you going to swap? You'll increment the left pointer and then swap whatever is there with the pivot. So your pivot is 30, so you'll swap 30 with 42. At this point, you are done with your quicksort. So see this is a sorted array. So this is exactly how quicksort works on an array. The next thing we have to do is we have to write the pseudocode and see the time and space complexities of this algorithm. So while writing the pseudocode, what are the things that we have to include in that? First thing, we should have a quicksort algorithm. We'll write a recursive algorithm because now try to understand when to go for a recursive algorithm. So this is a typical case where you have the same thing done again and again. That is, you have an array, you chose the partition, and after that you're going to run the same algorithm on both the partitions, which means you are doing the same repetitive task again and again on smaller subparts. So this is a clear-cut example of recursion, a specific place where you want to use recursion. So using recursion will make code readable. Moreover, it will look logical. It will look like you have written something in English only, because anyone can easily understand when you write recursion. Let us write the recursive algorithm for quicksort. So what should you write in the algorithm of quicksort? In quicksort, you want to start with A, then you have low. Low is the lowest index in the array, the starting index, and high. High is your largest index. So this is your initial array. Whatever is your starting point, this is what you called as low. Whatever is your last point, this is what you called as high. So you are going to start the quicksort. What will you do in quicksort? In quicksort, first thing you have to keep in mind, till what point should you keep running this? You should keep running this till the point you have at least two elements, because if there is only one element, that partition is already sorted. You don't have to run quicksort again because there is only one element. There should at least be two elements if you want to run algorithm and sort it. That is the logic. So you have to run till the point there is at least two elements. So how will you put that condition? If low less than high. This is only when you will run the procedures. If low less than high, what does it mean? There will be at least two elements if low should be less than high. First one index will be low, second index will be called high. If both are same, low and high are on the same element, that means there is only one element in the array. There is nothing to be sorted. So that is why we are putting the condition low less than high. If low is less than high, what should you do? First thing is you have to find the right index for the pivot. You have to partition this larger array by finding the right index for the pivot. How will you find the index for the pivot? For that, you will have pivot, let us say pivot position. Pivot position is equal to, we'll run a separate function for that. Let us call it partition. Partition of, in that function, what arguments would you need? You will need your array A, then you will need the low, which is lower index, then you will need high, which is the higher index. So this partition, after writing this quicksort, we'll write this partition algorithm. So as of now, just assume that I'll just write pivot so as to avoid confusion. This is the position of pivot, okay? Pivot underscore position, okay? This is the position of pivot. Position of pivot is what this partition algorithm will return. What will it do? It is supposed to partition your array into two parts by placing pivot at the right position and return you the position of pivot. This is what partition algorithm is supposed to do. So after partition, so at this point assume that partition is done and you know the exact position at which pivot is placed. What will you do now? You have to recursively run the same quicksort algorithm on both the partitions. You know this is the position at which pivot is placed. You have to run quicksort on the left subarray and the right subarray, right? So what will you do? Quicksort of A is the array. You will start from low. You'll start from low. Until which point should you run? This point is pivot's position -1. So whatever is the pivot position -1, that is the point till which you want to run this algorithm. First quicksort, and the second time you will run it for right subarray. How will you run it for right subarray? Quicksort of A. What is the lowest position? It is whatever is your pivot position, that +1 is your lowest position. So pivot position +1 to, till which point should you run? Till high index, whatever is your high index. So this is your quicksort algorithm. We are going to run the partition algorithm. This we'll write separately now. You should understand what is the quicksort algorithm. This is what quicksort algorithm is doing. Whenever you are having at least two elements in the array, you will partition the array and find out the right position of pivot. Once you get the position of the pivot, on the left subarray, you will separately run quicksort. Whatever you ran till now, you will also run quicksort on the right subarray. So the next thing, let us see how is partition algorithm written. So partition algorithm. This is the heart of quicksort, partition algorithm. Partition of A, low and high. These three things are what you need. What should be done in this algorithm? inside this, what should you do? You should initially choose a pivot. Conventionally, we choose the last element of array as the pivot. So first you should make this choice. After that, what do you want to do? You should keep 2 pointers, right? Then whenever the element is larger than pivot, you should just upgrade this pointer to the next element. If it is smaller, you should first increment this pointer, then you should swap the value at this pointer with whatever is in this pointer. So this is what we are going to do in partition algorithm. So the first thing, pivot. How do you identify pivot? Pivot is equal to array of high, that is the last element. We are conventionally taking last element of array as the pivot. So we chose last element as pivot. This is done. What is the next step? You want 2 pointers, I and j, let us say. So what will be your I? I will be outside your array. So how will you do it? Low minus 1. Low is the first element of your array. Low minus 1 means one step outside array. That is where I should stand. What is the next thing? You should have a loop which will take j from the first element till the last but one element. Why last but one element? Because last element is your pivot only. So you have to go till last but one element. How will you write this? For j is equal to, where should it start? In the low index. Low 2, till which point should it run? High minus 1, because high is your last index, which is the pivot. Till high minus 1, this should go. What should it do there? Let us take this upward. Okay, from low to high minus 1, when at each position, what is the work that should be done? You have to check whether the element pointed by j, is that element lesser than pivot, right? If it is larger than pivot, you don't have to do anything. You can simply increment. If it is lesser than pivot, that is when you have to swap the elements, right? So if it is larger than pivot, if you don't do anything, this loop is automatically incrementing j. So you don't have to specifically write any step for it, because this loop is running from low to high minus 1. So if you don't do anything, this loop will automatically increment the value of j. That is what happens whenever element is larger. That is, if this is your pivot, this is your I, this is your j. If you find that element at j is larger than pivot, you don't have to do anything here, because your loop will automatically increment value of j. But what should you do in case this is smaller than pivot? If the element is smaller than pivot, what do you have to do? You have to increment the value of I, then you have to swap the values at this I and that at j. This is what you have to do. So if the value at a of j, if this is lesser than pivot, in this case, what should you do? You should do I is equal to, that is I is the one which was standing outside. So you will do I equal to I plus 1. And then what should you do? You should swap the values of a of I and a of j. So swap a of I with a of j. So at this point, what have you done? You have completed the swapping, which means the smaller element is positioned in leftmost possible position. What will you do next? So whenever this complete loop is done, what can you assume? Whenever this complete loop is done, you know that all the elements which are smaller than the pivot, that are placed here, and your I is here. Whatever I is pointing to right now, that is the last element in your array which is smaller than j, pivot. And where is your j? J is already in the position just before your pivot. So at this point, j is no more required, because you are done with j. J already reached high minus 1, that is one element less than the pivot. Next thing you need is I, because you know I points to the position till which elements are smaller than pivot. What will you do? You will do I plus 1, and then you will put pivot here, and whatever is the element, you will put it in the place of pivot. So what are you going to do? You are going to swap. You will swap. So at this point, this for loop is done. Okay. So you will swap. What will you swap? You will swap a of I plus 1 with pivot. So A of I plus 1 is to be swapped with what is pivot? Pivot is A of I. A of I. So you will swap A of I plus 1 with A of I. So this means at this point you placed pivot correctly here. So whatever is in the right, they are larger than pivot. Whatever is in the left, they are smaller than pivot. What can you do now? You want to return the position of pivot. So you will return what is the position of pivot? I plus 1, because A of I plus 1 is where you place the pivot now. So presently your pivot is correctly positioned at I plus 1 position. This is your quick sort algorithm. So let us see this algorithm once in total. Quick sort part, you already understood what we are doing. The only part remaining was the partition part. In that, what we have to do? We have to find the right position for the pivot. So in that, what did we do? We started here. Okay, we started this partition here, and then we found the pivot element, which is the last element of our array. Then we started I, which is the left index, which will start from outside the array. J is the second index, which is the second pointer, which is the right side pointer. It is pointing to the first element of array. And till what point should it go? It should go till one element less than pivot. So it will come till here. J is supposed to come till there. What should you do inside the loop? Whenever the value pointed by j is less than the pivot, what should you do? You should increment I, that is, let us say j is at this point at this place. So if you found that value pointed is less than pivot, you will increment I here, then you will swap the values at I and j, which means the smaller element which was at j, that will now come to this position. So whenever you are done with j, whenever j reaches here, that is whenever this loop is done, what do you know? You know that wherever your I is presently positioned, let us say this is your I, till that point your array is sorted. Not sorted, those are lesser than pivot element, whatever are the values. What will you do then? You will swap A of I plus 1 with the pivot. So I is this, you will do I plus 1. It will come here, and then you will swap this value with pivot. So which means now pivot will come here. Pivot is placed at the right position. All the elements to the left are lesser than pivot. All the elements to the right are larger than pivot. Then what will you do? You again call quicksort on left side, quicksort on right side separately. So this is how quicksort algorithm is working. The next question is, what is the time and space complexity of this quicksort algorithm? So in order to understand this, first of all, you have to understand how this is working. It is partitioning. This is the basic logic. In case of merge sort, we had clearly derived how this division at the middle, that is, in that case, every time we were finding middle element. So division at middle, how was it leading to a total of log n levels? This we had clearly derived in case of merge sort. And one more thing we had seen there is total work done at each level. That is, if you are having then two subarrays, then you are again dividing this. You will have 4 subarrays. But at each level, total work done was order of n in case of merge sort. Same is the case of quick sort, because total work done is order of n, because you are again going from one side till the end. You have, let us say, you have pivot here. Till one element less than pivot, you are going to simply traverse. You are not going to traverse twice or thrice. You are just going to traverse once from this side to the other side, which means at each level, quicksort also does order of n work. Then the question is, how many levels are there? So in terms of levels, it is proven that in quicksort, generally, even if you don't get a clear 1:1 split, still the number of levels will still be order of log n only. So in total, in each level you have to do order of n work, and in total there are order of log n levels. So the total time complexity of quicksort will be order of n log n. So this is the average case time complexity of quicksort. See, best and average case both are order of n log n. If you ask for worst case, the worst case, there is a possibility that every time you choose a pivot. Let us say you are choosing the last element as pivot. And just assume that you are having an array which is already sorted. What will happen? Your last element is pivot. You know this is already sorted, which means last element will be the largest element. So you will keep checking from this point till this point. So you will do order of n work to come till this point, only to realize that the last element is placed at the correct position. What will you do? After this, your partition will be one side which is having n minus 1 elements and other side having nothing. So again, on n minus 1 elements, you have to run the same algorithm. So again, you have to do order of n work. So order of n work is to be done n times, which means worst case time complexity will be order of n square for quicksort. But quicksort mostly runs in order of n log n only, because it is proven that even if your split is 1:9, that is if you have 11 elements and after placing the pivot there is only one element on the other side and 9 elements are on one side, still time complexity is order of n log n only. So even in this sort of a worst split, still it is only n log n. If you are hitting a very rare scenario where complete array is already sorted or so that there is nothing on the other side, all the elements are on one side only, that is only when generally you hit order of n square. So in all practical scenarios, you won't hit that, because if you are given an unsorted array, worst case split will be 1:9. In fact, split will be better than that. So generally, quicksort works in n log n. That too, generally it works faster than merge sort. And that is it about quicksort. One more thing, you have to see whether it is in place algorithm, and also you have to see whether it is stable. So these two things we have to consider. So let us see time complexity as well. What is the time complexity here? Time complexity we had seen, it is order of n log n. What is the space complexity here? Space complexity, see, in best case what can happen? Your split, if it is in total order of log n, space complexity will also be order of log n, because when the split is your total height of it is going to be order of log n, your space complexity will also be order of log n, because space complexity is based on the recursion stack. What is recursion stack based on? Recursion stack is based on how many levels are you going to go down according to your split. And we already discussed that even if your split is 1:9, you are going to have only order of log n levels, which means your space complexity will also be order of log n, because the recursive stack will take up a maximum of order of log n, even if your split is 1:9. But if it is a case of, let us say, already sorted array, which is causing a time complexity of order of n square, though the split will be even worse, you may have an order of n space complexity. So similar to the case we discussed time complexity is actually order of n square for quicksort, and space complexity is actually order of n for quicksort. But for practical considerations, or generally in all practical scenarios, your time complexity will be order of n log n only, and your space complexity will be order of log n only. So this is the reality. So you can say average case time complexity is order of n log n, average case space complexity is order of log n, best case is also order of log n space complexity and order of n log n time complexity. But if you specifically go for the worst case, it is order of n square time complexity, order of n space complexity. See, generally whenever we talk about algorithms, we only talk about worst case. Here we are specially considering the average case, because the worst case is hit only in very corner cases. This is a special scenario. Otherwise, we'll always go for the worst case only. Okay. So that is it about quicksort. And is it an in-place algorithm? So what is in place? In place means all the works are done within the allotted array. And in quicksort, it is not like merge sort where we allotted extra array in order to do the operation. We did all operations inside our array only. See, we took a pivot, then we applied quicksort algorithm on the right subarray. We applied quicksort algorithm on the left subarray. But we did not allot a new array and copy all the elements. So space complexity, so even though space complexity log n is there for the recursive stack, this is an in-place algorithm only because all the work is done within the array. So algorithm is in place. It is not an out of place algorithm. It is in place algorithm. And what is it about stability? Is it stable? It is not a stable algorithm. What is the reason? It is not stable because you are doing these swappings. So whenever you do these random swappings, you don't know how the order of elements are going to be manipulated. So because of this swapping, it is not stable. So this is in place and not stable.